Very pleased to introduce Lourdes Agapito from UCL, who is going to be showing us fewer equations, I think, and a lot of very impressive real-world applications.
Thank you. I think this is working. Sorry, I just need to check. Yes, it is working. So thanks a lot, Andrew, for the invitation to be here today. So yes, there'll be far fewer equations. It's going to be a lot lighter, this presentation. But really what I'm going to try to show you today is, I've changed the title of the talk a bit to talk about this kind of road towards commoditizing the reconstruction of 3D non-rigid objects directly from either just single images or from monocular video. So video that we've taken just with a single camera. So we've now all got mobile phones in our pockets that allow us to do incredible things with 2D photos that we've taken. So we can take our phones out, we can take pictures of our children, we can find landmarks. So there are many 2D tasks that we can actually do on photos. We can then apply all these visual effects. So just applying 2D effects on pictures has really become a commodity, and we can do it every day with our mobile phones. We're much further away from being able to do this with our mobile phones in a very easy way. So for 3D reconstruction really to become a commodity, we're still quite far away from being able to do this. And I want to take you through maybe today what the challenges are, what the shortcuts that we've taken so far have been, and ideas on how we can actually be able to acquire these very dense and very detailed 3D shapes directly from monocular sequences or just from single images. So if we think about how the industry is actually solving this problem today, so they're really far away from having a practical solution. So here's a video of motion capture in action. So on the left you've got the markers on the subjects. You've got a camera that's directly looking at the subject. They're all wearing motion capture suits. So you can see that ultimately the quality that we get on the right is absolutely incredible, but it's not very practical. This solution is very far from being a commodity. So industry is finding all of these challenges, and they've taken many shortcuts so far. And what I want to show you is how can we maybe overcome these shortcuts and provide more practical solutions. So the first challenge that we have in non-rigid reconstruction is of course data association. So we need to find correspondences. We need to match points that correspond to the same points in the 3D surface across all the views. And the solution that the industry has found so far is of course to put markers. And obviously putting markers is a great solution for them, but it's very unpractical for the actors. And if we want to actually take this into the wild and being able to give people mobile phones and the ability to reconstruct. The second challenge is that reconstruction is an inverse problem. So if we just have a single view, of course we can have many different shapes that would reproject onto the same image. So this is a very important challenge, and the way that the industry has actually solved this problem is to introduce multiple views. So if we have multiple synchronized cameras looking at the same non-rigid object, we can then triangulate and reconstruct every single frame. And now we've got these very complex studios where we have maybe combinations of RGBD, so depth cameras, combined with RGB cameras. But typically we'll have very complex and difficult to maintain studios. The third challenge is something that I'm particularly interested in, which is that different objects will deform in different ways. So to have models that explain deformations that actually are useful across different object categories, that's actually a very hard thing to obtain. And typically what most people have done have been to specialize this into different categories of objects. So what works really well is to have a model of the human body, and for instance to have a PCA model that will actually explain the variations in the differences of shape, of identity of people, that can also then vary according to the pose, and then we just have far fewer parameters to reconstruct. And the same goes with faces. So part of the work that I'm going to show you is what if we actually want to reconstruct a whole image, where we might have objects for which we do have models, but we might have objects for which we don't actually have any models. So I want to talk about model-free non-rigid reconstruction, and I'm going to focus on this quite a lot because I think it's obviously a much harder problem to solve, but it's a very useful problem to solve, because very often in the real world we might not know exactly what's around us. And then the fourth challenge that I'm going to talk about is that we typically have a lack of training data in terms of 3D labels. So obviously, one obvious thing to do would be to say, machine learning is now offering amazing techniques and methods, with deep learning in particular, where if we actually have training data, if we have 3D labels associated with images, then we can just use all of this machinery and we can regress maybe 3D models directly from images if we have lots of 3D labels. But typically this is what we don't have. So what we have is what you see on the left. Very often we do have 2D labels. So people have painstakingly maybe marked the positions of some joints on the skeleton of human bodies. But what we typically don't have is dense 3D data or even skeleton data associated with images. So this is really something that we don't have. We have a lack of 3D annotations for images. So what I'm going to focus on today is a few different problems that are going to tackle all of these challenges, and I guess I'll show you that we're kind of one step maybe closer to commoditization. So the first thing that I'm going to show you is a lightweight and low-cost method to do model-free 3D reconstruction of non-rigid surfaces just from a monocular video sequence. And the second problem that I'm going to discuss today is how to reconstruct the 3D pose of a human, so how to estimate the 3D skeleton of a human just from a single image. And in fact, I'm going to talk about how to do this when we don't have 3D annotations. We only have 2D annotations on the images. And why do we actually want to solve this monocular problem? Why do we want to focus on really being able to reconstruct just from a single monocular stream? If we really want to tap into all of the videos that we now have on YouTube, on the internet, and we want to learn from these videos, then we need to really come up with unsupervised algorithms to be able to reconstruct the dynamic 3D world. So unless we're able to really deal with non-rigid objects, maybe very complex scenes where we have a combination of dynamic objects and rigid objects, but we don't have any previous information about what we're looking at, then if we can do this, then we will be able to learn from these very unstructured videos that are videos that come from YouTube. So ultimately, this is really what I'm interested in. I'm interested in unsupervised methods for 3D reconstruction so that we can apply them for videos that come from anywhere, where we don't necessarily have models, we don't have knowledge in advance about what we're going to find. So first of all, we're going to focus... Oh gosh. Okay.
Our approach direct slide we see color depth and normal input of a real-time scanner.
Not sure why, but I've turned the volume off, but it didn't actually...
Okay.
So I'll talk a bit louder maybe. Don't worry, Andrew, I'll just, okay. Okay, so I'm going to focus first on monocular 3D reconstruction of non-rigid surfaces from an RGB camera. So we were very inspired by this work. I think two of the authors of this work are actually sitting in this room, where they had an RGBD camera. So this is a very high quality depth camera, obviously aligned with an RGB camera. So they had an RGB stream and a depth stream, so two streams coming in, and they were doing this, very nice real-time, very detailed reconstruction of non-rigid surfaces. So the idea here is that first of all you construct a template of the surface, and then what you have to do is to actually fit this template and deform it so that it fits the current frame after deformation. So of course what we wanted to do was to say, can we actually solve this problem, but just with the RGB stream? So instead of having, the depth, we now don't have a depth value for the pixels. We just have the color of the pixels. So this is some work that we published in ICCV in 2015, and here you can see the quality of the reconstructions that we can get. So remember, the only thing that we have here as input is just the video. We construct a template initially, and then we're just deforming this template so that we match the current frame. And of course we're doing this using an energy optimization approach, and we're using a photometric cost. So what we want is that when we reproject a point onto the image, the color of that pixel is actually the same as the color of the corresponding vertex on the mesh, on the template mesh. So this is the definition of the problem. So we have a template that describes the geometry of the object in some rest shape, and then we also associate a color with each of those vertices on the template. And of course when we get the current live frame, this will be deformed with respect to the template, and we need to estimate a 3D warp field that will align or deform, in this case this dog, so that it's actually aligned with the current image. So what are we estimating here? We're estimating this warp field. For each vertex, we are estimating a 3D vector, a translation vector that's going to take us to the next position in the deformed frame. So we're using an energy optimization approach with a data term and a regularization term. And as I said before, what we're going to minimize is the dense per pixel model to frame photometric error. So in this case what we want is that if we found correct correspondences between the template and the deformed object, then of course the brightness of those two pixels should be the same. So we're trying to solve two problems at the same time. We're trying to find out the correspondences, of course, so we're solving this photometric problem of finding dense correspondences, and at the same time we're also deforming the template to take it to its new position. So that was the data term that we're using, just brightness constancy, and now we also have some regularization terms. And these regularization terms are quite common in the graphics community. The first one is an as rigid as possible regularization term which preserves local rigidity, and therefore we're preserving the detail. So locally we're modeling deformations as local rotations. So one of the things that you maybe need to realize here is that obviously now we're introducing three more variables here, because we're now saying we now have to model these local rotations as well. So now we've really got a 6 degree of freedom vector associated with each vertex on the mesh. So it's a 6 DOF parametrization. So we say locally we're going to preserve rigidity, and the other term that we have is a total variation term where we're preserving spatial smoothness. So when we look at these translations and we look at neighboring translations, then we're applying total variation locally to the translations, and in fact we're also doing this with rotations to smooth locally these local rotations. So obviously we end up with many terms. So we have an energy optimization approach. We want to minimize this, and of course what we're trying to estimate is this 6 degree of freedom vector for each of the vertices on the mesh. So it's a very high dimensional problem, and also an overall rigid rotation and translation. So on the top you can see the data term here. This is just obviously what I explained before, the classic photometric cost. Then we've got the as rigid as possible term, and these are the local rotations, which are new parameters that I need to estimate. And then this is the total variation term on the translations. We actually also apply it to the rotations. We also apply temporal smoothness because we have a video sequence, and we know that the surface is going to be deforming in a smooth way over time. Yes?
Do you require that these local rotations are consistent in some way, or not?
Consistent.
That means that if you rotate the points around a central vertex, then if you go nearby, the rotation has to be the same.
So the total variation will actually apply, and in fact that's the effect that you really see from the total variation on the rotations. So I haven't written it down, but we have a similar term for the rotations here.
But there's no hard constraint on the AI besides.
No. We just they have to be orthonormal matrices because we're parametrizing them as such. But apart from that, we don't have any hard constraints. There are no hard constraints in this problem at all. It's just an optimization where we're trying to minimize something that fits. And we obviously initialize the solution from the previous frame. So we're already quite close, and because it's a video frame, so we're taking frames at 30 frames per second, then obviously this is the main reason why it works.
Lourdes,
Yes?
like sometimes you're using a squared difference and sometimes not. Is there some reason for that? Like in your temporal smoothing, you're using a squared difference.
Yeah, so in this case, this is actually this is a Huber norm here. So this is total variation, but instead of using just the L1, we're actually using Huber so that it's smoother. And all of the other terms are actually so this term is quadratic. This is a Huber norm. This is actually a Huber norm as well, so that we're more just for robustness.
Why not say Huber everywhere? Why are you choosing some to be squared and some to be Huber?
I'm sure that we've played around with changing them. We're actually using Ceres as the solver, and Ceres is very flexible. It allows you to change the norm that you use for everything. So I'm sure that we probably started using a square norm for the brightness constancy term, and then we switched because we obtained better results. But I mean, obviously the total variation, we definitely want that to be L1, but we've used Huber because it's smoother. So the way that we acquire the template is that we just have a few initial frames in which we require the object to be rigid, and we take a few frames from that sequence, and we initialize just using multi-view stereo in this case. And these are some of the results. So this is actually a pretty hard sequence. The deformations here are very strong. And despite that, we're still getting nice reconstructions. So here you can also see that we're getting some of the folds on the face. So this is to show that we can also do kind of more articulated motion rather than non-rigid motion, and even sort of tracking hand motion. Here, the really hard thing with hands is actually acquiring the initial template. It's a very hard problem. You've got thin structures, and asking someone to hold their hand still is a really hard thing to do. very, very hard. It's much easier to do this with a depth camera. We could have done this with a depth camera as well. Okay, so we were actually very pleased with these level of reconstructions. Also, the nice thing about the previous algorithm that I showed is that it's almost real time. We can solve quite quickly, maybe 1 frame per second, and at times even faster than that. And the deformations that we're recovering are good, but something that we realized very quickly was that we're not actually exploiting all of the information that's in the image. So the question was, can we actually do better than what we were doing before by going back to the image and trying to recover high frequency details? So this is work that we did with Andrew, and we presented last year at VMVC. Really what triggered this work was to realize that our data term was also always trying to minimize brightness constancy. So we are assuming that when we project the same point in the 3D world onto an image, which is what you can see here, you can see in blue and in green the projection of these points on this on this rendering. So you can see that the brightness is actually changing over time. So our main assumption was that the brightness was constant, and in fact, because of the deformations, this is not actually true. So the way that we constructed this video was that we had some geometry. We've texture mapped the colors of the albedo of the face, and then we've actually rendered this face assuming that it's a purely Lambertian surface. So even though we've actually generated a purely Lambertian surface, brightness constancy doesn't hold over time. And the reason for this really is that it's because of the deformations. So because the surface is actually changing in orientation and the normals are changing over time, then of course the light is interacting with different surface normals, and that creates shading effects. So shading effects was something that we weren't taking care of, and of course if we don't take care of these effects, then the tracking completely fails. So I just remind you that this is actually a synthetic video, which is a purely Lambertian surface. And if we just do brightness constancy based tracking, you can see that the geometry that we recover is very, very poor, and particularly in the places where we have strong deformations. So of course what we needed to do was to actually go back to our model and to introduce the shading effects. So to model properly the reflectance model, so how the intensity in the image is being created. And of course we know that this is the product of the albedo and the diffuse shading, which in turn is the product of the normals, the surface normals, and also the illumination. And then finally we also allow for some specular highlights. So this is an additive term where we can also allow for specular highlights so that we can deal with surfaces that are not just diffuse. So this is now, a harder problem to solve for, because now we have the albedo here, we've got the normal directions, we've also got the illumination coefficients and the specularities. So we've got these two new terms that we need to solve for, as well as the albedo. And but it's actually, it has one very, very strong benefit, which is that, for instance, if the illumination changes over time, we can model changes in illumination. So this is something that we can recover. And of course, we can also deal with specular surfaces. So as I said before, these are now our unknowns. So the vertices, again, and the rotations, the per vertex rotations, an overall rigid rotation and translation. We model the illumination using spherical harmonics, so we need to recover the coefficients, and then we have a specular component as well, per vertex. So this is the cost that we're minimizing now. So all that we've done is that we've substituted the reflectance equation in the brightness constancy, and now we're actually minimizing by modeling everything properly. So here we have the albedo, here we have the coefficients of the spherical harmonics, and we have the normals of the surface and the specular component. So if we actually now solve this and we minimize this energy instead, now you can see that we recover the surface that you see here on the right. So the difference is huge, you know. And really what we're doing right now is that we're assuming that what's constant over time is the albedo. The albedo is what's not changing over time, and what, you know, because we are allowing the illumination coefficients to change over time and we're recovering the interaction of the illumination with the normals, then we can solve also for these shading effects that allow us to recover these very nice reconstructions, especially where we have the strong deformations. So this is the result of the new method, and this is the result of the old method. And this is really the most exciting thing for me. Now we can actually have surfaces that are specular, like the one that you see here. So it's got like a plastic type texture on the face. And we're now changing the illumination. We're moving the light source from one side to the other. If we do brightness constancy tracking, of course this fails miserably. Where we now model everything correctly, now we can actually recover the surface. Yep.
So you have some prior on specularities?
Yes, so we have a sparsity prior on the specularities. Yeah. Okay, so this is obviously to show that we don't just do faces. Obviously, you know, if we were only going to use this reconstruction method for faces, then we should have used a face model. Probably used a 3D morphable model. And here you can see that, you know, we can also recover other types of geometry. The only thing that we need to do is to acquire an initial template. So this is a very hard sequence because we've got lots of specularities and, you know, we're recovering the reconstruction quite nicely. Okay, so now I can go back to the problem I was trying to solve right at the beginning in the first slide, which is to say, you know, can we actually take videos of our children? So this is one of my daughters. You know, we just took a video in the garden, and here is a reconstruction with a textured, the texture kind of on top as well. And you can see that the tracking is working nicely because the texture is being tracked very nicely. But you can also see how we're recovering the geometry, so all of these kind of wrinkles on the forehead, etc. And it's probably easier to see some of the geometry in this other video. Okay, and here we have another video where you can see that we can recover. So the other nice advantage is that now we can also recover high frequency details because we've actually decomposed into shading and albedo. We can reconstruct very, very high frequency details. So we've actually got all of the wrinkles on the face and we're tracking those nicely. Okay, so you know, this is just a slide that I wanted to show to show everyone the kind of evolution of this area of non-rigid structure from motion. So, you know, at the beginning of the 2000s, we were kind of down here. We had batch methods. We decoupled tracking and reconstruction, and we could only reconstruct a few points. We moved on to dense reconstructions, and now I've shown you how we can jointly do the matching by solving a photometric optimization and also recover very high frequency details. So we're recovering now the physical properties. So we really have moved on a lot in the sense of recovering dense 3D surfaces from monocular video. So now I'm going to switch modes a bit, and I'm going to talk to you about the problem of reconstructing the human pose in 3D just from a single image. So this is work that I've done with Dennis Tomei and Chris Russell at UCL as well. And we've in this work we're actually taking advantage of deep learning but we're also using a lot of geometry within this approach. So I think it's an interesting way of how to use geometry so that we can train a deep network with fewer labels and only with 2D labels rather than requiring 3D labels. So we called this work Lifting from the Deep, and here what we're trying to do is that from a single image, we just have a single RGB image in this case, and we have no temporal information. We're trying to do two things. We're trying to extract the 2D skeleton, so we're trying to find the skeleton that fits the human in 2D, and we're also simultaneously we want to reconstruct this into 3D. So the output of our system is not just the 3D pose, it's both the 2D and the 3D pose. We're reconstructing both things, or we're estimating both things. So we're reasoning jointly about these two things. And the reason for this is that these two problems are actually very coupled. So obviously to be able to reconstruct the pose into 3D, we need to know whether 2D joints are in the image, or it's useful to know whether 2D joints are in the image. But also, if we know what the pose is in 3D, we can also improve our 2D estimations. And this is also quite an exciting thing. So in terms of related work, if you look at the current papers that are working on 3D pose estimation from a single image, you'll see that obviously all of them are using deep learning, but most of them are actually using 3D labels. So we have a data set where we have images, and we actually have 3D annotations of the skeleton for each of those images. And this is really what we wanted to avoid. And the reason for this is that whereas there are many data sets that have 2D annotations of human pose, and we can take advantage of all of these, what we really don't have a lot of is images that are associated with 3D skeletons. So instead what we do is that we have two completely independent sources of training data. On the one hand, we've got images that are associated with 2D annotations, and on the other hand, we've got 3D mocap data. And this 3D mocap data, we don't have the images for those. We just have a corpus of 3D mocap data, and what we do is that we have these two completely independent sources of training data, and we're going to learn a probabilistic 3D pose model for the 3D data, and we're going to use that within our deep learning approach to be able to solve for the problem of 2D pose estimation. So I'll show you how we do this. So the first thing that we do is that we have this motion capture data, so we have many different poses for different people, and by pose we mean the 3D coordinates of 17 joints on the human body. So it's 17 times 3. That's the data that we're aligning. So the first thing that we do is that we build a probabilistic 3D pose model, and with this model what we can do now is that if we knew where the 2D joints were, this model is going to allow us to reconstruct the pose and lift it into 3D. So we're going to learn a model that will allow us to go from 2D joints to 3D joints. This is what we're going to do. And using an energy optimization approach. So how do we learn this probabilistic PCA model? So we're going to model this with PPCA. So the first thing that we need to do is that we need to align all of the poses. So we denote these poses by this big PI. So these are each of the poses. And what we're going to do is that we're going to align these poses so that they're all aligned and looking in the same direction. At the same time, we're also going to estimate a PPCA basis to model them. So the first thing that we need to, so our unknowns are the mean pose and a shape basis. So we learn some basis shapes that will span the space of possible poses. Of course, we also need to learn the basis weights, and we also need to learn the rigid alignment that will align all of the poses so that they're all looking in the same direction. So this is all the data alignment. So we solve this energy optimization here, and as you can see, we're solving for the rigid rotations, for the mean pose, for the basis weights, the shape basis, and sigma is the noise here. So these are the poses before alignment, and this is a visualization of what the poses look like after alignment. And what you can notice here is that now we've got some very nice kind of clusters. So we've got a cluster over here that are standing up poses. So this is another cluster where we've got sitting down poses. These are kind of lying down and crouching poses. So now we've actually aligned all of the data. They're all looking in the same direction, and at the same time we've learned this probabilistic PCA model.
Excuse me,
Yes?
this is a 2D plot, but of what exactly?
Yeah. This is just a visualization, we've done PCA and just 2D, two-dimensional visualization.
Principal directions.
Sorry?
What is the principal directions for the
Yes, but this is just a 2D visualization, right? So the second step is that, so rather than using a single PPCA model, in fact what we do is that we use a mixture of PPCA models. So we then do clustering, and we use, in this case we're actually using 4 PPCA models, and we found that this is actually a better way of representing the space of human poses. So rather than using a single PPCA model, we use a mixture of them. Okay, so with this we've actually now got a model, and with this model, if we're actually given, if we know the 2D landmarks, then we can solve this optimization problem to estimate the rotation and the coefficients that will lift this 2D pose into 3D. So now, we know the basis, we know the mean pose. So now every time that we get a new image, if we have the 2D positions for the joints, we can actually reconstruct the pose into 3D by estimating just the pose and the coefficients. This is an energy optimization to lift 2D poses into 3D. Okay, so now we're going to use a deep learning architecture, and as I said before, what we're going to do is that we're only going to use 2D labels. So the loss that we're going to use is going to be only on the 2D pose. So we want our 2D poses that we're estimating to be the same as the ground truth poses. So what does this architecture look like? So we take an image as an input, and the first layers are actually feature extraction layers. These are all convolutional layers. And we also have some 2D prediction layers that are going to give us some heat maps as an output. So each of these heat map will tell us our belief of where each of the joints is going to be. So we get 17 images back, and these are heat maps that will tell me where each of the 17 joints, relief maps for each of the 17 joints. So this is what this part of the architecture looks like. It's a convolutional architecture, and then it predicts these belief maps. So what we can do now that we've predicted these 2D belief maps, we can actually collapse these belief maps into just a single 2D pose estimation for each of the joints. And using our probabilistic 3D pose model, we can then lift into 3D, and we can reproject back onto the image. And we generate a second set of belief maps, and these are reprojected. So they've gone into 3D and they've been reprojected back. So what we're saying is that, okay, when we take the 2D pose that's been predicted by the convolutional layers, when we lift it into 3D and we reproject it back, it should reproject back in the place where we measured the ground truth, right? So now we've actually got 2 different ways of estimating 2D poses. One is coming just from the convolutional layers, and the other one has actually been lifted into 3D and is coming back into 2D. So here we've got two different belief maps, you can see them here, and we're just going to also learn some weights on how to combine them. So we fuse them, so we take a weighted average of these two estimates and we fuse them, and the weights that we use for the weighted average are also being learned by the network. And of course at the end what we produce are some final belief maps, and this is where we apply the 2D loss. The 2D loss is the difference with the ground truth labeled 2D poses. So just to make it slightly more complicated, now this architecture is actually a multi-stage architecture. We don't just have one stage, we don't just finish here. We then concatenate multiple stages, and the output of each of the stages becomes the input also to the other stage, as well as the input image. So we have two inputs for the second stage and onwards, the input image and also the prediction that came from the previous stage. So this is actually, these kind of multi-stage architectures have been shown to work very well in the case of human pose estimation for 2D estimation, because it's actually giving us a bit like a coarse-to-fine approach. So we're already giving an initial estimate, and we can actually refine the estimations as we go through the stages. And you can see that in this slide here. So in this slide you can see two things. You can see, so these are the input images, this is the pose, and you can see that, you know, we've got occlusions here. This is the really difficult thing about 2D and 3D human pose estimation, that we have self-occlusions. So we can't see the elbow, we can't see the right knee, so it's hard to estimate them. So here you can see this is the evolution through the stages of the estimation of where the landmark is for the left wrist. So this is the final estimate, which is correct, but if you realize we started off confusing it with the right wrist. So first of all, the heat maps are telling us that the left wrist is actually on the right wrist. And of course this is the main problem that we have as well in human pose estimation, that there's no difference in what they look like, so we have this symmetry problem. But of course, because we're reconstructing in 3D at the same time, then at some point, so this skeleton, if we try to reconstruct a skeleton where the pose is actually being confused, the left and the right joints are being confused, then this will give me a 3D pose that's very far off from my manifold of allowed 3D poses from the probabilistic model that I've learned. And then, you know, I can actually help to get back to the left wrist and to come up with a good 3D estimation in the end. So this is what the final architecture looks like. So we have an image as an input, and of course as an output we're getting 2D poses from this network. And of course we can always do this final lifting at the end and recover the 3D pose. So here are some examples on the human 3.6M data set, which is the data set where everyone evaluates in the vision community. So you can see here that, you know, there are some self-occlusions, and the estimation of the network is quite good for most of these poses. How to fast forward. So these are harder poses because we've always got fewer examples of those.
This is completely frame independent?
Yes. It's just frame by frame. There's no temporal consistency here. Yeah, and despite that, it's actually, you know, it's not that bad. Okay, so of course when we submitted this paper to CVPR last year, we were better than everyone else on the human 3.6M league table, which is what you need to do to get your paper accepted to CVPR. I mean, now, you know, a year later, these errors have maybe gone down to 60 something millimeters. So, you know, we were already pretty competitive just a year ago. And this is comparing on other protocols with other methods. So here's the more interesting thing, probably, that you know, we've actually learned all this data, and now we can reconstruct very, very hard poses. So these are hard poses both in 2D and in 3D, right? It's very hard to detect the position of the joints in 2D, and these are also very challenging poses to reconstruct. So this is the MPII data set, for which we don't have any ground truth 3D data, only ground truth 2D. So we trained the 2D on MPII in this case, and the 3D is obviously reconstructing quite nicely. And then, of course, the great thing is that, you know, can you actually then take your own videos and reconstruct the pose in 3D? So this is one of Niloy Mitra's students at UCL. He was working a completely different paper to do with something to do with how people interact with geometry and the geometry around us. He took our system and extracted the 3D pose, and is actually doing a very nice job. And then finally, we now have an EU project where we're working with roboticists, and this is a video that's been taken from a humanoid robot that's observing people who are doing maintenance tasks in a warehouse. So this is, you know, pretty tricky footage. Get back, yes. So this is difficult footage to work with because obviously, you know, these people are wearing kind of very, you know, dark clothes. They're difficult to detect. And in this case, we did actually apply some temporal constraints, some temporal smoothness constraints, and we can reconstruct the pose quite nicely. Okay, so then, you know, something that's nice is that we were looking at humans, but you can also apply this to other types of objects. So as long as you can model the object category with some landmark positions that are semantically meaningful, and then you can do PCA on the 3D data, then we can also extend it to other object categories. So we've also been looking at chairs, so we're now reconstructing chairs as well, and looking at other object categories, faces as well. And you know, finally, I think something else that's exciting is that we don't just have normally just 2D annotations of skeletons. You know, we can also, for instance, obtain silhouettes. So there are richer sources of 2D information that we can extract easily from images, and therefore, you know, this is something that we should be using as well. So, you know, we could then, if we were extracting silhouettes, and we were then imposing constraints on the reprojection of the silhouettes, then we could reconstruct dense models for the humans. And this is something that we're working on right now. So this is maybe a bit related to what Andrew presented yesterday, so using silhouettes in the context of 3D reconstruction. And then, of course, you know, something that we also want to do is to go towards a self-supervised system. So we still need supervision here. We need to be told, we need ground truth values for the 2D landmarks. And what we want to do next is to really push this towards a self-supervised system. And what we're working on right now is to use multiple viewpoints at training time, and to then the 3D pose needs to satisfy the constraint that, you know, if we're reconstructing from multiple viewpoints, all of them have to agree on the same 3D pose. So that's a great self-supervision signal. So we can use that to do 3D reconstruction, and this is what we're working on right now. So So trying to use as few labels as possible, that's really where we're moving towards. So I got a few more minutes, so I want to talk about another piece of work that we're doing right now. So this is work that I've done with my student Martin Runz, and we presented this work at the robotics conference at ICRA this year. And this is something that I'm getting quite interested in. So being able to reconstruct dynamic scenes where we have multiple moving objects, and being able to do this in real time so that robots can actually interact with the 3D world. So I think I've spent a lot of my career doing all these 3D reconstructions and trying to do reconstructions that were as dense as possible. But then the question is, why? Who cares, really? And I think when you start working with people in robotics, you realize that, a robot is receiving all of this geometry, but we need to give the robot the geometry in a way that it can actually do something with it and understand the world around it. So something that we're doing right now is to try and segment the scene into semantically meaningful objects, but allow and reconstruct them, of course, so reconstruct the rich geometry, but to allow also these objects to move. So not to reconstruct just the static scene semantically, which has been done before by many groups, but to allow dynamic and semantically meaningful reconstructions of the world. So the motivation really is to allow robots to interact with humans, or to interact with a scene in a much better way. So something that of course is very obvious is that if you look at SLAM systems, so SLAM has been solving this problem of simultaneously trying to find out the position of a camera at the same time as inferring the geometry of the world. So if we look at how a SLAM system would, how it would solve a problem like this, where we've got two different motions, we don't just have the motion of the camera, we have an independently moving object in here. Of course, the resulting geometry is not going to be correct because we've made the wrong assumption. We've assumed that the whole world is static, and it's not. Another option is that we could actually detect these as outliers and we could just eliminate them from the scene. But that's not what we want either. What we want is to be able to segment different moving objects and to be able to reconstruct these and reconstruct the rich geometry of each of these objects independently. So this is what we're doing in this work. We've called this work co-fusion. In some ways the principle is quite simple. So we acquire, every time we acquire a new frame, this is a real-time system, we acquire a new frame, we track the objects that we are currently tracking in our system, and we perform some type of segmentation. So the nice thing is that this segmentation can either be semantic segmentation, it can be segmentation based on motion, so motion segmentation, it can be based on surface normals, so geometric segmentation. It can be, we can use multiple cues to actually do this segmentation. And each time a new label, a new object comes in, we spawn a new model, and then we follow that by fusing the geometry. So we're maintaining a few different models for each of the different objects that we've detected in the segmentation process. So, as I said before, there's two ways in which we can segment the scene, or maybe more than two. But one way would be to actually segment objects based on their motion. So the static background is now in grey. We've labelled it in grey, and then we're identifying different objects because they move independently. And you can see that we can segment them, and we can obviously give them different labels according to which are the pixels that are moving coherently, that have the same motion. So this is nice, but perhaps even more interesting is if we can take a scene that contains various objects, and we can run an instance level semantic segmentation algorithm, such as mask RCNN, for instance, And then we can segment the objects based on their labels, and as you can see here, we can then maintain all of these labels, and we can reconstruct the scene, and now we have an interpretation of the scene at the object level. So this is much more interesting for a robot than just having, lots of different objects. So something that you can see here is that when we take the labels just from the semantic segmentation algorithm, you see that the labels are actually leaking a bit. The boundaries are not very, very good quality. So what we're doing right now is that we're combining geometric and semantic segmentation. So here you can see the result of a semantic segmentation algorithm. This is mask-RCNN, which is a very, very recent deep learning-based approach. And here is also the result of a geometric method that's looking at surface normals and is looking at where the boundaries of objects are based on the coherence of the surface normals. And we're combining the two. And here we now have labels. We know that this is a keyboard, we know that this is a ball, we know that this is a teddy bear, and that this is a clock. So now a robot can come and can actually interact with the scene. Or something else that we can do is that because the objects can move, now we're picking up the teddy bear. You can see that a person is picking up the teddy bear, and we can continue to track the teddy bear. And we can even ignore, for instance, labels that we're not interested in. So if we don't want to track the human hand, we can, because we've identified those labels as belonging to a human, we can ignore those and we can stop tracking those labels. So this is a much nicer way to actually present a reconstruction, and a much better way to interact with a scene. If we don't just have just circles in this case, or voxels, if we can actually have semantic labels, then we can really interact with a scene and do things with a scene. Okay, so that's the end of the three things that I wanted to show you today. I also wanted to talk a little bit about, maybe the future and what comes next in terms of this road towards commoditizing dense 3D reconstruction in the context of dynamic scenes. So of course something that we all want to happen very soon is to be able to do augmented reality and virtual reality in the case of non-rigid scenes, right? So this is work from this was the holoportation project from Microsoft, and this was a really amazing attempt at reconstructing non-rigid surfaces in real time and be able to use this in with a HoloLens, so in an augmented reality environment. For this project, they needed to have many different RGBD cameras inside a room, and the room where the other person was. Technologically, it's still, very, very challenging to do this, but I think that we have shown that we're kind of slightly closer to being able to do this, maybe with mobile phones. But as I said at the beginning, this is really what I find very exciting. It's, if we're given a video that we've downloaded from the internet and we want to really understand what's happening in all these videos, we maybe want to classify them or archive all of our holiday videos. It's important that we're able to analyze the motion of dynamic objects and non-rigid objects, and then we'll be able to learn in 3D properly from these video libraries. And finally, I have to say that working with roboticists is a pretty humbling experience. We've been working on this problem of non-rigid reconstruction, showing our models and going, look, these are great, they look amazing, but they have to be useful, they have to be happening in real time. And it's really, for me, it's been a real learning curve to interact with roboticists and to see what can we give them in terms of geometry that's going to be useful for them. So the final thing is to thank my team who've done all this work, and also, the lovely European Union for all the funding, and Microsoft as well. So thank you.
So you built your probabilistic model based on mocap data
Yeah.
that was available. So I was wondering how much variation is in the mocap data. So like the skiing pose probably is not in there. So how critical is this?
Yeah, so I mean, obviously the mocap data that we've used is limited, but what we didn't do, and we should have done, is that we could animate. With this mocap data, we've already got like a rigged skeleton of a person, so we could then go on and animate this and create lots of synthetic data. We're just creating 3D positions. It's not.
That's kind of another question.
Yeah,
Especially
so
for human pose, you can do lots with synthetic data.
exactly. So we haven't used any, we haven't exploited any of that, and we really should, because that's a great avenue. Yeah. Yes.
How differentiable did you make your 3D interpreter?
Yeah. So it is differentiable, and you can do back propagation.
But there are a few ways to do it, right? You can just auto-diff the code, or you can use implicit function theorem. I mean, there's a bunch of strategies.
Yeah. I mean, we have actually derived we've written down the derivatives ourselves, not auto-diff in this case.
Right.
Yeah.
But it is an iterative algorithm, the 3D interpreter. Yeah.
Actually, yeah, we can. So the way that we do it in the end is that we actually, we don't actually run it as an iterative algorithm. We try lots of possible solutions. It's super fast. So we try lots of possible solutions, and then we choose the one that has the lowest energy. So in the end, it's we're not running it as an iterative algorithm.
Right, and then you compute the derivative at that point.
Yeah.
I mean, if it would be pure PCA, you could differentiate the energy minimization. But since you have a mixture, I guess this makes things quite difficult.
Yeah. But yeah, this is what we do. That we don't run it as an iterative algorithm in the end. We do obviously right at the end, because that's when we have the 2D pose and we lift into 3D. But inside the network, it's we generate different possibilities, and then we choose the one with the lowest energy. And also the 2D, for instance, finding out the pose of the person, the rigid pose, that we have a closed form solution for that. So, because we assume that we kind of know what the vertical axis is, so it's just a rotation around the y-axis.
What people would probably do these days, and you might have thought about it as well, is predicting the network, letting the network predict the 3D joints, using them to, just projecting them into 2D for your one part of the loss function, where instead of using a probabilistic models to lift, use like GAN or so to find out whether the predicted pose is real or not.
Yeah, so there's recent work from other people, from Katerina Spragiadaki, for instance. They're using GANs to predict, to produce like a possible pose, and we decided to do it this way.
Good.
Yes.
Just for the segmentation part, were you using which cues in the end you were using, geometric or?
So the very final video that you saw, we were doing this one here. It's a combination of both. So we're combining. You can see the semantic segmentation. That's mask RCNN. It's an instance level semantic segmentation algorithm that's been trained on the COCO data set. And what we found was that if you look at the boundaries, they're not so good. No, actually, what I'm showing here is the combination of both. So this is the combination of the geometric segmentation with the semantic labeling. So what we found was that the geometric segmentation gave us really, really good boundaries, really nice boundaries. The semantic segmentation leaks, and then you just start leaking into the background. It doesn't give us a very good segmentation. So we're combining both So for the boundaries mostly is where we're using the geometry and internally the...
So for the geometric part, excuse me if that's
Yeah,
a weird question, so
No,
is
no.
it done at the learning stage or just as some kind of post-processing, like the geometric part, or?
The geometry is done on a per frame. This system is a very traditional SLAM system. It's not, the only thing is we're using an off-the-shelf deep learning system to give us the segmentation, but it could be anything, right? To give us the semantic segmentation. The geometry segmentation is produced at every frame by analyzing the surface normals and looking at big discontinuities in the surface normals in the neighborhood. And that's how basically what that allows us to do is to predict the positions of the boundaries. And this is what you see here. These red are, that's the prediction of where the object boundaries are. So the only thing is that the geometry, it gives you very nice boundaries, but it over-segments. So for instance, it might over-segment the legs of the teddy bear and the torso if it's sitting upwards. And the semantic segmentation gives you meaning, and it gives you also a nicer segmentation overall.
So this looks like Kinect style input data.
Yeah,
So how is the geometric segmentation dealing with missing data with occlusions?
We're doing this. This is done. The geometric segmentation is done in the depth image.
Yes, but is there anything in particular happening to address the occlusions in the missing values in the depth map?
The black ones.
Yeah, because
Well,
they are
oh,
occupied
you
quite
mean-
often exactly at the boundaries.
Mhm.
So I was wondering if any means of
In-painting on the depth image or something like that. To be completely honest with you, maybe my student actually did that. I don't know. I'm not sure. It's possible. I mean, I know that we've run a bilateral filter first on the depth image, but yeah, it's possible that there might be some. Yeah, I think that's quite common to use in-painting first to actually fill in the gaps where you don't have information.
Okay, I detect a conflict of rumbling stomachs and
Yes.
minds, so we'll